What the WITS plus Barcelona quantum structured light breakthrough actually is. The core idea is quantum structured light, using more than 1 degree of freedom of a photon to encode information space plus time, and sometimes frequency, color, polarization, etc. The Nature Photonics review by Andrew Forbes, WITS, and colleagues describes this as engineering photons, in space and time, to access high-dimensional, multidimensional entanglement and high-information capacity photons, enabled by a rapidly improving toolkit that now includes on-chip, integrated photonics solutions. DOI.org WITS University. What multiple streams per photon means, in precise terms, a single photon can live in a Hilbert space with dimension d and gt. 2, a qubit, not just a qubit. If you can reliably prepare, transmit, and measured orthogonal states, you can encode up to log 2 d bits of classical information per detected photon in principle. Capacity depends on noise, loss, and detection. This is what people loosely describe as many streams in one photon. Common channels inside one photon. Spatial modes, for example, orbital angular momentum, twisted light, temporal modes, time bins, ultra-fast pulse structure, spectral modes, frequency bins, colors, combinations, hyperentanglement, entanglement across multiple degrees of freedom. The review frames this as moving from a virtually empty toolkit 20 years ago to compact, efficient on-chip sources that can create, control these states. WITS University. Why structured photons can carry way more information than regular photons. 2 reinforcing reasons. Higher dimensional alphabets instead of binary 0, 1. You can use 0, d-1. The WITS release explicitly points to high-dimensional encoding alphabets, enabling more information per photon and better resilience to noise. WITS University multiplexing across degrees of freedom. You can stack encodings, space plus time plus frequency, which can multiply capacity, if you can keep crosstalk and loss low. Important reality check. This does not magically beat Shannon limits on a given physical channel. It's about exploiting more orthogonal modes and better encoding, decoding, so the practical bits per detected photon can rise a lot for some channels. 3. The security guaranteed by physics. Part. What's true, what's hype? Quantum key distribution, QKD, can provide security grounded in physics, measurement disturbance, no cloning, but real systems still have implementation vulnerabilities, detector side channels, source imperfections, etc. Unhackable is best read as properly designed QKD can be information theoretically secure, assuming the implementation matches the model. Structured light helps because higher dimensional protocols can improve noise tolerance and can raise key rates per detected photon in some regimes, but it doesn't remove the need for careful engineering and security proofs. WITS University. 4. Topological quantum states. Why they matter. One of the most exciting parts mentioned in the WITS UAB coverage is adding topological structure to quantum states to make them more robust to perturbations, noise, obstacles, distortions. WITS University. Think of it like error-resistant knots in the wave function. The information is stored in features that are harder to accidentally destroy. This is a real research direction, and Forbes's group has related work on topology and robustness in entangled states. The review cites this line of work. DOI.org. 5. The biggest bottleneck. They admit distance structured spatial modes can be fragile in real channels, turbulence, fiber mode mixing. The WITS release is blunt. Long-distance reach remains low for some structured light approaches compared with simpler degrees of freedom like polarization. Hence the push toward better degrees of freedom, better chips, and topological protection. WITS University. 6. How this connects to quantum networks, and distributed quantum computing. Structured light fits into the roadmap like this. Quantum networking, quantum internet. Use photons to distribute entanglement and/or keys between nodes. Distributed quantum computing. Entanglement links let separated processors behave like one larger machine, in principle, but the networking stack needs higher rates, lower loss, and better repeaters. Structured photons can help by increasing per-photon information capacity, allowing richer entanglement structures, potentially improving resilience, especially with topology. The Nature Photonics Review positions the field at an inflection point, driven by both bulk optics and on-chip toolkits that make deployment more realistic. DOI. Org 7. About the Starlink is using quantum networks. Rumor I couldn't find credible. Primary evidence that Starlink itself is currently operating a quantum network. What does exist? SpaceX missions are frequently used as rideshares for quantum communication experiments, e.g., proposals, coverage around ISS-hosted entanglement, quantum comm experiments. The Quantum Insider. So, the grounded take is SpaceX can be part of the launch ecosystem for quantum comm, but Starlink is already running quantum internet. Appears to be speculation, not confirmed engineering reality. 8. The memory chip breakthrough that cuts transaction energy. What it likely refers to. Your description matches a broad, and very real, trend. Cutting the energy cost of moving data between compute and memory. The von Neumann bottleneck. 2 recent, concrete examples from reputable institutional coverage. MIT. December 11, 2025. Stacking active components on the back end of a chip. MIT describes stacking multiple active components, so data doesn't have to travel as far between logic and memory, reducing wasted energy. MIT News 3D chips that vertically stack memory plus compute. Science Daily covered a 3D chip concept that stacks memory and compute elements to speed internal data movement, and, typically, reduce energy per operation by shortening interconnect paths. Science Daily Why this matters for quantum too. Even quantum computers need massive classical support, calibration control electronics decoding and amp. Error correction, very compute heavy. So, energy-efficient memory, compute architectures are a big deal for supercomputing now and scalable quantum later. 9. Putting it all together. The 2-engine acceleration. You're noticing what you're sensing is real. Progress is compounding from 2 sides. Engine A. Better photons for networking, high-dimensional encoding, more bits, key per photon in some regimes, topological robustness on chip sources and amp. Processors bringing lab optics toward deployable photonics. DOI.org. Engine B. Better chips for the classical workload. 3D integration, compute near memory, new materials and back-end stacking, less energy per inference, per transaction, per memory access. MIT News together. They support secure communications, distributed computing, data center efficiency, and eventually, more practical quantum network plus quantum compute stacks. Global Robotics Corporation.